Hi, and welcome to the live stream of the German Aerospace Center. My name is Charlene Rogal. I'm here at the Ramstein Air Base in the DC-8 Flying Laboratory. On our ECLIF mission, together with our partner NASA, we'd like to study the particle emissions of alternative fuels. And right next to me, NASA scientist Richard Moore. Hi, Rich.
Hello.
Could you introduce yourself?
Hi, my name is Rich Moore. I'm a scientist at NASA's Langley Research Center in Hampton, Virginia, in the United States.
What is your specific job here on this mission?
So I'm an airborne atmospheric scientist, and I'm interested in understanding how aerosols or particles that are emitted by jet engines in the atmosphere go on to evolve in the atmosphere, and then also influence their ability to form the contrails that we see up high in the sky as well as clouds.
So what is this ECLIF, especially ECLIF mission now all about?
Right, and so we're delighted to be working with DLR again. NASA is and DLR have a long partnership in understanding the Earth's atmosphere and our environment, as well as the environmental impacts on aviation. And so what ECLIF and the NASA counterpart NDMAX is trying to understand is, as we change the fuel that's being burned in our aircraft, the fleet is transitioning towards blends of biofuels. Okay. And so we want to understand how changes in the fuel composition change the particles and gases that are emitted by the engines.
Okay. So you just mentioned contrails. So how do the contrails affect or have an impact on the climate?
Right. Well, contrails have a huge impact on climate. And so, in fact, some of the recent modeling work that has come out of DLR suggests that contrails today, just the ones that we're able to see up in the sky, maybe today, this week, this month, have a larger impact on Earth's climate than all of the carbon dioxide emitted by aircraft since the first powered airplane flight. So that's a huge effect. And so even as CO2 accumulates, greenhouse gases accumulate in the atmosphere, the impact of these contrails trapping heat and reflecting sunlight back into space is having a huge effect on the Earth's energy balance. And so we don't understand those processes. We don't understand the processes by which contrails evolve into natural cirrus clouds. And so we're trying to understand that link. And that's what this project's all about.
So that we can understand the research better, of what do contrails consist?
Right, so contrails, or condensation trails, are little ice crystals that are high in the atmosphere. So that when we burn jet fuel in these very efficient, highly efficient jet engines, most of the carbon in the fuel is completely combusted and forms carbon dioxide and water. So just our typical combustion reaction. But a small amount of that, a very tiny amount, maybe 1 part in a million, goes on to form soot particles, the tiny black particles that we see on the ground from cars and buses. And so those tiny soot particles serve as nuclei, or the focal point on which water can condense and form an ice crystal. And so the theory goes, as you reduce the amount of soot produced by the engine, you might reduce the number of ice crystals that form in the contrail. And so we're trying to understand that link, the link between the particles, and then the water vapor condenses on those particles to form the clouds and the contrails.
And that's why you have different mixtures and also mix the kerosene with alternative fuels.
That's right, yeah. And so we have a fairly good handle on the emissions from traditional petroleum-based fuels. There's been a number of experiments spanning the last several decades. But given concerns about the global energy supply and oil supply, different countries like the European Union and the United States and others are really starting to consider biofuels as an alternative to petroleum-based fuels. And so what we're doing here at NASA and DLR is we're conducting the fundamental process-based research that we can then hand off to policymakers, and then they can go on and understand how the science and economic choices that they make will affect society.
And we are here right now, live, in the research aircraft. So maybe you can explain a little bit. The ATRA from the DLR flies in the front,
right,
and the DC-8 in the back.
That's right.
So what is the job of the DC-8?
Right. So the DC-8 is NASA's flying laboratory, and so you can see behind me there's a whole host of people and a bunch of racks with all sorts of instruments measuring the particles and the gases and these contrail and cloud particles. And so I'll give you a tour as we walk through and point out some of the highlights. In addition, we have a intrepid crew of maintainers. You can see they're crowding around in the cockpit up here, maintenance, working to keep a plane flying so that we can continue doing research every day. And so we've done a number of flights, 4 flights so far. We expect to continue with 5 more flights this next week. And so these are the guys who really make the magic happen to make sure that we can fly every single day. And that's really, really important.
Yeah, people are really excited that the DC-8 is actually here in Germany. That's pretty special. So I would love a tour.
Yes. Okay.
That's cool.
As we come back from the cockpit on the camera's left here is the navigator station. So you can see that this is where they plan the flights.
Okay, wait a second. Maybe we rearrange the situation a little bit.
Perfect. And so this is the navigator station. This person is charting the route, making sure that we have the required clearances, because we're doing things that are non-traditional, where normally a jetliner takes off, it flies a straight line, and then it lands. And we're not doing that. We're flying racetracks, we're flying all around, we're targeting contrails, we're targeting planes. And so that makes a little bit of a headache for our partners at air traffic control, but they're happy to work with us. And so the navigator sort of makes sure that all works.
So maybe we can even just now explain the process a little better so that everyone can imagine how it actually works. Because you said you have to fly a certain maneuver, so that you just explain what happens up in the air. Just really quick to wrap it up, and then we go back to the stations. Thank
you. So in Germany, there are a number of temporary restricted areas, TRAs, that are reserved by the military, and we, working with DLR, have access to that. And so the ATRA and the DC-8 take off typically around 11 a.m. local time. And then we fly about an hour up to one of the TRAs. And so we have our choice of 4 different locations throughout Germany, 2 in the north and 2 in the south. And the scientists are looking at the meteorology, we're looking at the forecasts every day to understand which one of these reserved airspaces we want to reserve for the coming day's flights. And so what we're thinking about there is we're trying to understand where will we see contrails, where will we see natural cirrus. And so what we're looking for is a balance. We want to be able to see contrails, but we won't want the atmosphere to be so moist that it's hard to distinguish the contrails from all of these clouds. And so we're looking for this sort of Goldilocks condition. And so once we have that, we file the flight plan, we take off, and then when we get up to that area, we're just doing circles. So if you were to look at this on a map, the ATRA would be doing a circle, and then the DC-8 would be flying right behind it, doing the exact same circle, roughly about 5 to 10 nautical miles in separation distance behind that.
So the DC-8 is basically trying to catch the contrails.
That's right, and it's harder than it seems. Even though the pilots have a good visual reference, the contrail isn't static. It doesn't look like the line that we see from the ground. It's undulating up and down and all over the place, and so the pilots have to maneuver the aircraft in order to put our sampling inlets into that plume. And so one of those sampling inlets is right above us here.
Okay.
And so this is how we sample the atmosphere. So we're a pressurized aircraft. Obviously, we want to make sure that the air in the cabin is not leaking outside. And so we have to draw air in from the outside in very specialized ways. And so we do that with specialized gas and aerosol inlets. And so this is one of them here. It's just a simple tube that sticks out the top. And on the other end of that is a scoop that ingests the air. It slows it down, and then we sample it in through this tube.
Oh yeah, we will also see that later outside, right?
Yes, we'll see that shortly. And so then the flow, the air that's drawn into the cabin, passes through a network of tubes and is distributed to the instruments in the racks that you see off to our left here. And so we have a number of particle instruments. These are the instruments trying to characterize the number, the mass, and the size of the particles that are emitted by the jet engines. And what we're looking for here is changes in the number and mass of particles that are emitted when we burn the biofuel blend versus the conventional petroleum-based fuel.
How many mixtures do you have?
So we have a number of mixtures. 4 mixtures are being studied by the E-Cliff project, and we're flying 3 of them. And so the goal of that is to understand certainly the petroleum-based reference fuel, but also we want to understand two different blends. We have a 50-50 blend of the biofuel and the petroleum fuel, and then we have a 70-30 blend as well. And so we're trying to understand, as we change that percentage of biofuel, how much does that change the emissions? So these are the particle instruments. And so you can see Eddie Winstead, one of our scientists at NASA, busy trying to get the instruments checked out for tomorrow's flight. And so you can see right now we've got particle counters and particle sizers. He's looking at a size distribution of the particles. And so the particles that he's looking at now are roughly about 50 nanometers in size. That's 10 to the negative 9 meters. Okay. Very, very small particles. And so it's a very challenging measurement to make, and Eddie's one of the best people we have to do that.
And here on board we have a combination of DLR and NASA instruments, right?
That's right. And so the front rack in the front was DLR, and this is another one of the DLR racks. This one is targeting not particles, but the gases that are emitted by the aircraft engines. And so unlike the tubes that are used to collect the particles, these require specialized tubes, and so this is a Teflon tube.
Why is it Teflon?
Well, just like Teflon, you use Teflon on frying pans to prevent things from sticking. The gas molecules that are flowing through here are sticky. They want to find the wall and stick, and so we want to make sure that they get to the instruments in order to be measured. And so what they use is big tubes. They're made of Teflon, so an anti-stick material, and they're pulling just a tremendously high flow in order to limit the amount of time it takes to get from the inlet above us down to the instruments. And so that's one of the challenge of these particular, especially the gas phase instruments. So you can see all sorts of vacuum tubing. A lot of our job is plumbing, looking for leaks, making sure everything is leaks. I mean, we have a number of scientists in the cabin. And you know, people are breathing, and so there's a lot of moisture in here, and so any sort of leak from the cabin will contaminate our measurements because the atmosphere is very clean outside.
This place looks really cozy. What happens here?
Right, yeah. So this is the flight station for the flight director, and so so we've been talking about the scientists that are involved with the ECLIF and NDMAX experiment. We're at our stations. We're making our measurements. We're all on headsets chattering constantly because we're excited about the data that we're seeing in real time.
How many people are actually on board?
Typically, we fly with a complement of about 15 scientists. But when we do transit, when we came over from the U.S., the plane was full. Every seat was full. And so the people who sit here, the left seat is the mission director, and the right seat is his assistant. And what they're doing is they're monitoring the power that's drawn by all of the different racks. And so they have full control over all of the different experiments. If there were to be a problem, if there were to be some smoke or a pump failed or something that was concerning for safety of flight, they have the ability to immediately shut down power to that rack, which is really important for a NASA flying laboratory. In addition, I mentioned the scientists. You know, we're excited about our data. We're talking all these ideas, and the pilots are trying to fly the plane. And so what the mission director does is it serves as a firewall between the scientists who are excited about the science data and the pilots who actually have to pick one route and follow it. And so what this mission director does is it takes all of the input from the scientists as well as the ultimate feedback from our principal investigators, our mission scientists, and he's the one who tells the pilots, okay, this is where we're going to go. This is the altitude. This is the direction. And that way, that when the pilots are up in the cockpit flying the plane, they have a single voice directing them from instead of 10 or 20 voices in the back. And so that makes it manageable because, you know, it's a plane. We can't stop and wait and think about what we want to do. We always have to be going somewhere. And so the flight director plays an integral role in making sure that happens.
So all the scientists here, do they have then headsets and communicate, or how does it actually work?
Well, it's incredibly noisy on the plane.
Wait.
A lot of different pumps and airflow handlers, and so we all have headsets, like what's shown here. And so we can put these on, and they're noise canceling, and we have a microphone, and so we can key the mic in order to talk to each other. And so this is the principal way that we communicate with the mission director as well as with each other. And so during a typical flight, everybody's seated, we're strapped in, we have harnesses, we have 5-point or 4-point harnesses that ensure that as the plane is rocking and rolling in the contrails, that we're all very safely away from our hard racks, and then the headsets allow us to communicate with each other.
So you sometimes get, of course, really excited about your data, and then you chat.
Yes, absolutely. And that's really important because, the pilots, in many cases, can see the contrail, but under some conditions where we're sampling, there is no contrail. We're sampling clear air. And so the pilots are flying, in essence, blind. And so they can feel turbulence, they can feel changes in the aircraft behavior, but they can't see the screens that we see back here. And so when we enter the plume, we can immediately see it on our instruments, and we can provide feedback over the headsets to the mission director. We're in it, we're seeing that was a good spike, or maybe that was not so good.
It's all about communication.
Exactly, yep. And that's really what ensures that we're getting the good data that we expect.
How many instruments are here on board in total, actually?
That's a great question. Well, we have, there's about 10 different science racks, and each rack is roughly a different research group, either within NASA, DLR, or our partners at the universities.
All right.
So we can continue back a little bit further and look at some of the additional instruments. These instruments here...
I'll just send you the mic.
Oh, perfect. So the instruments here are measuring, in addition to measuring gas phase water vapor in some of these silver flow tubes to the left. The computer monitor on the right is looking at detailed information related to the cloud properties. And so as we'll see when we go outside, we have a number of different probes that are not in the cabin. They're actually mounted on the outside of the aircraft in order to measure the cloud properties, the contrail properties. And so the people sitting at this flight station are looking at this laptop, looking at the screen, trying to understand what the properties of those clouds are. So as we continue back, we have another aerosol rack. We have another aerosol rack. We're starting to get into some of the mass spectrometers. So this is one of them, looking at the aerosol particles. And behind us are two other mass spectrometers looking at aerosols and gases. And what these do is that they take the particles, they take the gas ions, they bring them inside, and they hit them with high energy electrons, high energy protons, and they break them apart. And so then they send them through a mass spectrometer, in essence, to put the pieces back together of the puzzle and try to infer what the thing was that they just exploded in the mass spectrometer ionization chamber. And so these give us a feel for not number, not size, not mass, but the composition of the particles. What are they made of? Are they sulfates? Are they organics? Are they nitrates? Are they hydrocarbons? And so a lot of the detailed chemistry is provided by these instruments back here.
Okay. So where's usually your spot?
Oh, I sit up in the front. So we passed me right at the beginning. And so we all have these nice one of the comforts of being on the DC-8 is it's a larger aircraft, and we have these really, in addition to the nice noise-canceling headsets that keep us sane over the course of an 8 or 10 hour flight, the seats are also very comfortable and allow us to move around and also work on laptops and with notebooks and things as well.
Yeah, on one hand, it's clearly a flying laboratory, but on the other hand, it kind of looks like also a passenger machine.
That's right.
It looks kind of comfortable with the luggage cabins.
That's right, yeah. And so as we move to the back, so for many of the missions that NASA does, the entire plane is full. But for this mission in particular, what we're focused on is the pilots are being able to put the inlets, put those sampling tubes in a very specific spot. And in order to make that happen, it's really important that they be on the top of the plane at the front. And so that really limits the number of instruments that we can have as we start to come to the back here. And so what you have here is the full complement of instruments that we've chosen to target this specific science problem, but there's still a lot of room on the DC-8. And so we jokingly refer to this region as business class. So this is where most of the maintainers and the technicians and the people who are coming over, keeping the plane operating, when we fly over from the U.S. and when we fly back at the conclusion of the project, those people are sitting back in these seats as well. Okay. And so, and we also put instruments back here, things like pumps and gas cylinders, things that don't need to necessarily be close to the inlets.
Okay, but even on DC-8 in business class, of course, there are instruments.
That's right. That's right. Yeah, we're trying to keep this thing as full as possible.
Yeah.
And there's a lot of trade-offs. We want to minimize. I talked about the sticky gases. We worry about particles being lost to the walls of the tube as well. We try to keep the tubing lengths as short as possible for the samples we're making. But when we're doing a calibration or something that involves, say, the cylinders here with the specified gases, we don't have to worry too much about the line length. So we can put them back here in business class and run long lines up to our instruments in the front. And so that's helpful. That keeps the weight and balance of the plane in line as well with the way the ops engineers like it to be.
What about we walk back there and then maybe take a quick look outside?
Okay, sure. So I just want to highlight, being
Wait a second.
Being on a laboratory like this is a great experience. We have a world-class, state-of-the-art facility, but it's not, without its creature comforts. And so when you're on an 8 or 10 hour flight, being able to have a hot chocolate or heat up a bowl of chili in the microwave, for example, or the technicians usually have the coffee pot going pretty much steadily throughout the flight, and so that can be the difference between freezing up here in the high altitude or warming up with a warm drink or some lunch. And then in the back we have 2 full service restrooms like you might see on an airliner as well. So the flights are long, and this aircraft is specially equipped in order to carry those out.
When is your next flight? When you're heading out next?
Well, so we are delighted to be here in Germany at Ramstein Air Force Base through February 3rd. We'll go home. This aircraft will then be deployed for another project at the end of February. So we'll hurry to get all of our instruments off so that next project cannot get on the DC-8. And then our instruments will be headed out on a C-130 for another project in the North Atlantic in March. And so it's
fully booked.
it can be a little bit of a non-stop schedule sometimes, but we're looking forward to an opening this summer to really dive deeply into the data, because that's the fun part.
Nice.
In addition to being in the field and collecting the data, having some time to actually look at it and understand the scientific results and write papers and give presentations is so important, because we're out here collecting this data. We're taxpayer funded. The data is publicly available, freely available, and so that's the real key is making sure that the data and information that we collect here is accessible to the public and accessible to policymakers.
Yeah, nice, really important. All right, since we've seen so many interesting things inside, maybe we could also take a quick look outside.
Sounds great. So we're outside now. You can see the view of some of those inlets that I was telling you about, and unfortunately they're covered because of the rainy weather. We cover them with these red bags in order to keep precipitation and snow off of the measuring sensors. But we can get a feel for where those tubes that I pointed out on the inside of the aircraft stick up through the aircraft skin to the outside. And so
the golden and red ones?
Yeah, so let's start with the most ones forward on the top. And so those are the silver ones. And so that's that aerosol inlet that I described, the one that draws the air in. And then moving backwards to the golden ones that you mentioned, the one that's closest to us, the long one with the pointy cone on the backside, is a cloud probe. And so that's one of the measurements that's being made of the contrail ice in order to size and count the number of crystals that form in the contrail. Right beside it, the very tall one with the very tall red bag, is the gas phase inlet. So that's the one with that Teflon tube that's sampling all those sticky gases. That's right. That's right. And then as we move back the plane, we have smaller inlets, so it's hard to see, but just above the engine here, there's a white little pylon sticking out of that gold-colored window plate. And so that's one of the instruments, one of the mass spectrometer samples off of that inlet. They have a little Teflon tube that sticks out to get outside the boundary layer of the aircraft. And so it's a big plane. We've got instruments mounted on the fuselage, and then we also have instruments mounted on the wingtips. And so you can see here, again, with the red bags removed before flight stickers, these are some of the cloud probes measuring the contrail properties.
Yeah, maybe we walk over there really quick.
And so it's a little hard to see the features of these, again, because they're protected against the elements. But essentially what each of these instruments is doing is that there's two arms that stick out. And they're parallel to each other. And in between the arms is a laser beam. And as the ice crystals move through the laser beam, they scatter light in little blips. And so that happens hundreds of times per millisecond. And they count the number of blips, and they also count the way the light is scattered in order to back out the size distribution of the ice crystals. And so we have a number of different probes, each targeting a different size range. Okay. So some probes may target, say, 1 micron to 50 microns, and other ones may target larger particles. So a micron is 10 to the negative 6. So we're talking about 1,000 times bigger than those soot particles that I described on the aircraft. So we're measuring nanometer-sized soot particles. We're measuring micron-sized ice crystals. And then even smaller gas molecules. So there's a lot of different instruments measuring a lot of different scales. Yeah.
Right. Well, I guess thank you for your time and all the insights and all the explaining.
Sure. Thank you for joining us. This has really been fun. We're always delighted to be here. We're delighted to be here in Germany. We're delighted to be NASA is delighted to have been invited by DLR to take part in the eClif campaign. And again, it's been a wonderful partnership over these past many years, and so we're looking forward to future projects.
Cool. Thank you, Rich.
Thank you.
Yeah, of course, if you want to get more information, we keep you updated. Just follow and check out our Twitter account, and you could also hashtag FlyDLR or hashtag FlyNASA. There you will find more information. Bye-bye, that's it for now.